Hello friends, we have derived the governing equations of semi-classical electron dynamics and discussed about the limits of semi-classical model in detail. We have found that compared to the free electrons, velocity of Bloch electrons differ, particularly for the electrons with wave vector close to the zone boundary. In this lecture, I am going to introduce a very important concept of hole. Concept of hole is a remarkable achievement of the semi-classical model, which can give satisfactory explanation for anomalous Hall coefficient in some metals. First, let me show that a completely full band does not take part in electronic transport by using some simple arguments. We apply an external electric field and solve the equation of motion. H bar dk dt is equals to force, charge of electrons times the electric field. We have to find how k is changing as a function of time, and this is how the k changes as a function of time. Let us imagine that we have a partially full band. In this diagram, the open circles represent unoccupied states and the filled circles represent occupied states. This is how the states are occupied at t equal to 0. Now, at this point of time, we switch on an electric field in this direction. This is how the occupation of the state changes when we switch on the electric field. Note that before applying the field, equal number of positive and negative k points were occupied. After applying the field, more number of positive k points are occupied. As a result, net change of k is positive when field is applied in this particular direction. Now, let us consider the case of a completely filled band. In this case, delta k is equals to 0 even in finite electric field, as shown here. As a result, we cannot get any current in case of a completely full band. In conclusion, completely full bands cannot take part in transport process. So far, our discussion is based on 1D cartoons. Let us look at some more realistic picture. This is how the partially filled bands of monovalent atoms look like in case of a monovalent metal. I have assumed a 2D square lattice. This is how it looks like if we draw the corresponding constant energy Fermi surface in reciprocal space. The Fermi surface is circular. The magenta shaded region is the filled portion of the reciprocal space. The black point in the center is the gamma point, and the red points are adjacent reciprocal lattice points. The third diagram shows a divalent solid with some band gap. As a result, the first band is completely full and the second band is completely empty. This is an insulator. The second diagram is a divalent metal where both first and second band is partially full because of band overlap. Fermi surface is fragmented, part of it lying in the first Brillouin zone and part of it in the second Brillouin zone. Electrons in the first and second solid will take part in transport process because of partially full bands. In case of the third solid, electrons cannot take part in transport process because of the completely full band. Transport is possible if we can excite some electrons from the first band to the second band in some way, for example, via thermal excitation. Let us derive the expression of current density of Bloch electrons. We start with the regular expression of current density given by J equal to minus E times rho times V. Minus E is the charge of electron, which is a fundamental constant. Rho is the carrier density and V is the velocity. We have to determine rho and V for Bloch electrons. Velocity is given by the first derivative of energy with respect to K. Note that velocity depends on K as well as on the band index N. There is no simple explicit expression for energy of Bloch electrons. As a result, there is no simple explicit expression for velocity as well. Now, let us try to get the electron density rho of Bloch electrons. We know that volume occupied by a single K point in reciprocal space delta K is equal to 8 pi cube divided by V, where V is the volume of the solid. Now, consider a volume dk about a point K in the reciprocal space. Number of K points in volume dk is dk divided by volume occupied by a single K point, that is delta of K, which is equal to dk divided by 8 pi cube by V. Now, each K point can hold up to 2 electrons according to Pauli's exclusion principle. Thus, to get the number of electrons in volume dk, we have to just take this number and multiply it with 2, and we get 2V by 8 pi cube dk, which is equal to V by 4 pi cube dk. Thus, infinitesimal volume element in reciprocal space dk contributes dk divided by 4 pi cube electrons per unit volume. Now, current density is minus E, which is the charge of an electron, times dk divided by 4 pi cube, which is the number of electrons per unit volume, times V of k, which is the velocity of electrons. We have to integrate over the occupied states. Let us try to understand what do we mean by integration over the occupied states. This implies that integration needs to be carried out over the entire region contained within the Fermi surface. For example, in this case, over the entire Fermi circle as shown by this hashed area. On the other hand, in case of the second figure, integration needs to be carried out over the entire fragmented region, part of which is lying in the first Brillouin zone and part of which is lying in the second Brillouin zone. Before proceeding further, let me compare the steps leading to current density calculation for Bloch and free electrons side by side. In case of free electrons, this is how momentum changes when an external electric field is applied. And this is how the crystal momentum changes in case of a Bloch electron when an external electric field is applied. Energy of free electron depends quadratically on wave vector k. For Bloch electrons, there is no simple explicit form. Energy depends on k as well as the band index n. In case of free electrons, velocity depends linearly on wave vector k. As a result, we have a simple expression for velocity at time t given by h cross by m times kt, and we get k from this equation such that velocity at time t is h cross by m k0 minus e t by h bar. In case of Bloch electrons, we do not have any simple explicit form of velocity. Velocity has to be calculated from the first derivative of energy with respect to the wave vector. Finally, the current density is obtained by integrating V in k space over the Fermi sphere of radius kf. Since we know the exact form of V from this equation, we can easily evaluate this integral. In case of Bloch electrons, there is no simple explicit form of V. V is obtained from the first derivative of energy with respect to k. Thus, the expression for current is minus E integral dk by 4 pi cube. Since we do not have any simple explicit form, we have to use this 1 by h bar del E divided by del k. Thus, current will depend on the energy dispersion relation of Bloch electrons. In this case, the Fermi surface need not be spherical. Thus, we have to carry out the integration of V over the occupied region in reciprocal space. The occupied region need not be spherical. It can have some very complicated shape. Let us first try to get the current density of free electrons. This is how K changes when we apply an electric field E. When electric field is 0, Fermi circle is centered at the origin of the K space. When an external electric field is applied in this direction, center of the Fermi circle is shifted from the origin of the K space. From the equation, you may conclude that the center of the Fermi circle keeps shifting towards the right as long as the field is on. However, that does not happen because steady state is attained very soon due to scattering. Thus, we replace T with a constant tau, which is also known as the relaxation time. Thus, in the steady state, delta K is equals to minus E times electric field times tau divided by h bar. From this, we get the steady state velocity as minus E times electric field times tau divided by m. Now, let us find the current density by evaluating this integral. Note that the velocity v is a constant, which is equal to charge of the electrons times the electric field times relaxation time divided by mass. Since v is a constant, let us bring v out of the integral and rewrite j as minus e times this integral tk by 4 pi q. Note that the integral is over a Fermi circle of radius kf, such that we can put the limit as 0 to kf. Integral 0 to kf dk must be equal to the volume of a sphere of radius kf in k space, such that we can write j as e square times electric field times tau divided by m into 1 by 4 pi cube into volume of the sphere with radius kf. And this is equal to e square times electric field tau divided by m times kf cube divided by 3 pi square. Note that this term is equal to rho, the electron density. Thus, we can rewrite this equation as rho times e square times tau divided by m times the electric field, where this term rho e square tau by m is the electrical conductivity sigma. Now, let us calculate current density for Bloch electrons. This is not as simple as free electrons, and I want to highlight the difficulties very clearly in this slide. This is how crystal momentum changes when we apply an electric field E. We have to evaluate the integral of velocity over the occupied portion of the reciprocal space to get the current density. This is where the calculation differs from free electrons. Let us first consider a partially full band such that we have a nice circular free electron like Fermi surface as shown here. You may think that at least in this case, we can easily evaluate the integral like we did for free electrons. However, it is not necessarily true. Remember that in case of free electrons, velocity is a linear function of k. As a result, it is not too difficult to evaluate the integral to find j. However, in case of Bloch electrons, there is no simple explicit form of V. Thus, we have to always calculate V from the first derivative of energy with respect to K. As a result, even if we have a free electron like Fermi surface, we may not be able to treat the problem as a free electron problem. In case the Fermi surface extends beyond the first Brillouin zone, it becomes even more difficult. For example, in this case, both the first and second band is partially occupied. Velocity also depends on band index n. As a result, we have to calculate J separately for both the bands. For example, when we evaluate the integral of Vk over the occupied regions in the first Brillouin zone, then we get the current from the first band. And when we integrate Vk over the occupied regions in the second Brillouin zone, then we get the current from the second band. In conclusion, unlike free electrons, current density has no simple explicit form in case of Bloch electrons. Now, let us look at the most important message we can carry forward from this slide. This is a completely full band. There is no band overlap. In K space, the first Brillouin zone is completely occupied and rest of the Brillouin zones are unoccupied. We know that completely full bands do not take part in transport. As a result, if we evaluate this integral over the full Brillouin zone, we should get 0. Based on our discussion so far, let me introduce a very important concept of hole. We already know that completely full bands cannot take part in electric transport, and if we carry out this integral over the entire Brillouin zone, which represents a full band, we get 0. Now, let us split the integral over the full Brillouin zone into two parts. Integral over the occupied region plus integral over the unoccupied region. That is, for example, let us consider a simple case where we have a free electron like Fermi surface. The blue region of the Brillouin zone is occupied and the red region of the Brillouin zone is unoccupied. Splitting the integral over full Brillouin zone into two parts, we get minus E integral over occupied and integral over unoccupied. And this should be equal to 0. Now, we can rewrite this equation by bringing the integral over unoccupied states to the right hand side, such that we can just write it as this. Since the left hand side is equal to J, the right hand side also has to be equal to J, the current density. Thus, current density can either be obtained by calculating this integral over the occupied states or by calculating this integral over the unoccupied states. The first one is known as the electron description, as the charge carrier is negative. The second one is the hole description, because if you note carefully in this equation, the charge carrier is positive. In conclusion, current produced by levels occupying electrons of charge minus E is same as the current produced by unoccupied levels if we fill them with particle of opposite charge, that is plus E. Remember that only charge carriers are electrons. However, sometimes it is more convenient to describe the current to be carried by fictitious particles of positive charge known as holes. In a band, such fictitious positively charged particles or holes occupy the levels unoccupied by electrons.